In this video, we're going to be talking about pump down systems, pressure switches, and solenoid valves. Not necessarily in that order, but they all have to do with the pump down system in refrigeration and air conditioning. So let's start with the basics of the solenoid valve. The solenoid valves are a mechanical and electrical valve. The mechanical part is in the refrigeration or water line. Okay, that's a valve. That's the valve assembly right where my mouse pointer is. And the electrical portion is the coil that is attached to the top of the valve. The valve in the closed position is not powered, and the flow of liquid is being blocked by the plunger in the down position. Now, this is for a normally closed solenoid valve. A normally open would act in the exact opposite way, but we don't see those used that often. So in the closed position, the coil does not produce any magnetic field as it is not powered. So it actually allows the plunger to stay down. So this is a normally closed pilot operated valve, okay? So we have a plunger here, okay? The valve is blocking the flow of liquid because it is not powered. Once the solenoid valve opens, okay, when the coil is powered, the coil generates a magnetic field and pulls the plunger into the up position. This allows fluid flow through the central passage of the valve. Okay, so once again, now I have the valve is open. So what we do is we actually allow fluid in that little hole there. And once the pressure builds up down here, this main valve assembly will move up. So the solenoid valve is now, the pilot is open. Okay, and then once the pressure equalizes, that main body moves into the up position, allowing fluid to go through. That's what we talk about with a pilot operated valve. And quite honestly, that's why we can use 24 volts or 120 volts to open a valve against 400 psi of pressure. In refrigeration, solenoid valves mainly have two uses. We use them for a hot gas bypass defrost, which is one of the type of defrosts, and we use it in a pump down system. So the solenoid in the pump down system is used in the liquid line prior to the metering device and after the receiver. The solenoid is in the normally closed position. When the thermostat calls for cooling, the solenoid opens. This releases the refrigerant into the liquid line and raises the pressure of the system. A pressure switch senses this pressure increase and turns on the compressor. When the call for cooling is complete, the thermostat de-energizes the solenoid closes and blocks the flow of refrigerant into the liquid line. The refrigerant gets pumped into the receiver, which is mounted after the condenser coil. Once the refrigerant is pumped down into the receiver, the pressure on the system drops. Once the pressure is dropped to a predetermined point, the pressure switch opens and shuts off the compressor. So the thermostat controls the solenoid. It does not control the compressor. The pressure switch controls the compressor. The purpose of a pump down system is to prevent liquid refrigerant from migrating to the evaporator on the off cycle. Okay, liquid refrigerant will always go to the coldest point in a system. And in most refrigeration systems, the box temperature is below the outside temperature. If liquid refrigerant is in the evaporator, it will be sucked in as a liquid into the compressor on startup. Liquid refrigerant in the compressor can break valves, crankshafts, and cause premature compressor failure. Commercial freezers are low temperature, and commercial refrigerators are medium temperature. Both are common to have pump down systems for commercial application. Low temp systems and medium temp systems, the evaporator is the coldest point of the system when the system is off, so the liquid refrigerant will migrate to those points. So here we have a pump down system where it's in the off cycle. Okay, when we look at this diagram, I have my condenser, it's off. I have my evaporator. That fan in a commercial system is most often running. I have 20 psi on the low side, 100 psi on the high side. My liquid line solenoid is off, which means my refrigerant is trapped for the most part. between the compressor and the solenoid valve. The way we're able to do that is because the receiver is right there where my mouse pointer is, and that holds the majority of the refrigerant that's in the system. So we open this valve when our thermostat calls for cooling. Okay, so now we have the solenoid valve that's energized. We are now allowing liquid refrigerant into my metering device, and my pressures on the low side are going to start coming up. Okay, so now it's starting the cycle. My condenser fan is still off because the pressure switch has not energized yet. Once we get to a predetermined point, my low side pressure energizes or closes a pressure switch, which energizes the compressor and the condenser fan motor. So now my system, my box temp is satisfied. We close the solenoid in the liquid line. That's off, de-energized. My compressor is continuing to pump until we pull this pressure on the low side back down to a predetermined set point, which is around 20 psi. And then my condenser fan and my compressor shut off. So again, the compressor is controlled by a pressure switch, not by the thermostat. The thermostat controls the solenoid valve. So this is a schematic of the pump down system. Okay, you'll notice here that I have two pressure switches controlling my run winding on my compressor. Okay, and of course the condenser fan is probably wired in here someplace as well. But I have a low pressure and a high pressure. The low pressure, okay, is a set based on what we want the system to pump down to. I don't want it in a vacuum because I don't want to run a compressor in a vacuum, but I want it at a very low pressure so I know that there's going to be no liquid in the evaporator. My thermostat right here, which is a cooling thermostat because it's facing down, controls my solenoid valve. Okay, we can tell this is a solenoid valve because it has a coil and an arrow through it. That tells me it's a solenoid. So sequence of operation, okay, when the thermostat calls for cooling, okay, it energizes the solenoid valve, which opens a mechanical portion of a valve that's attached to that coil. Okay, as the pressure rises, my low pressure will close. My high pressure is a safety. Okay, so that has nothing to do with the pump down cycle, but it has to be there. When my low pressure closes, it energizes the condenser or the compressor and the condenser fan. So pressure switches are used to start and stop the electrical loads such as motors and coils. Pressure controls contain a bellow, a diaphragm, or a board-on tube to create movement when the pressure switch is changed, when the pressure is changed. When used as a switch, the bellows or tube is connected to a linkage that operates the electrical contacts. When used as a valve, they operate the valve directly. The electrical contacts are the components that actually open or close the circuit. The electrical contacts either open or close with a snap action on a rise in pressure. The pressure switch can also be used to sense a pressure differential and be designed to open or close a set of electrical contacts based on this differential. In other words, the difference between pressures at two different points in the system. The pressure switch control can either be an operating type control or a safety type control. It can either operate at low or high pressures depending on the type of design. Now, when we talk about an operating type control, okay, that's like it's attached to a thermostat, opens a valve, and allows our system to run. A safety type control would be like the high pressure switch, that if something goes wrong and the pressures go too high in a system, it's going to open and shut everything down. Safety type pressure switches are lots of times do have a manual reset. Okay, in other words, a button somebody has to push to get the system to start working again. Pressure controls can sometimes be recognized by the small line running to them for measuring fluid or refrigerant pressures. Pressure switches are manufactured to handle control voltages or line currents to start a compressor up to 3 horsepower maximum. If you get above 3 horsepower on a motor or compressor, you have to then use a contactor or some other type of relay device to operate those compressors based on the pressure control. It's just an extra step in the circuit. The high pressure and low pressure controls in the refrigeration and air conditioning industry are the two most widely used pressure controls. Some pressure switches are adjustable and some are not. Some controls are automatic reset and some are manual reset. In some pressure controls, the high pressure and low pressure controls are built into one housing. The point or pressure setting at which the control interrupts the electrical circuit is known as the cutout. The point or pressure setting at which the electrical circuit is made or closed is known as the cut-in. The difference in the two settings is known as the differential. Okay, so a compressor will shut off at a cut-out pressure. The compressor will start at a cut-in pressure. The difference in these two settings is known as the differential. So when we look at a pressure switch, okay, if my cut out is 5 psi, my cut in is 20 psi, the differential is 15 psi. Okay, so in a pump down system, the compressor is at this time off, the solenoid's closed, we energize the solenoid, release the refrigerant. The compressor will not start until the low pressure side reaches 20 psi. System's running, cooling the box. The thermostat gets satisfied, de-energizes the solenoid valve. My cut out, the compressor will continue to run until the cut out of 5 psi is reached. Okay, and we keep those far enough apart so that the compressor doesn't bounce around and start to run again as the refrigerant warms up and the pressure goes up. Okay, so we can also use a pressure switch to control the box temperature. Okay, some of the older equipment doesn't have thermostats. So let's say we want our box temperature to be an average of, let's say, 15 degrees. We use our cut out at 5 degrees. We use our cut in at 20 degrees, and we have a differential of 15 psi. So the box temperature will always be between 5 and 20 degrees. And that difference is usually, it's right there around the 15 degree point. So the pressure switch, again, has a movable diaphragm. Okay, as a rise in pressure, the diaphragm is pushed up. Okay, so the electrical components, the switches, are attached to the top of the diaphragm. Another type of pressure switch uses a board-on tube. Okay, the gear is fastened to the end of the tube with linkage. Rise in pressure, the entire tube is pushed and moves the gauge, needle, or electrical contacts based on that. Pressure switches are in 4 different ways, okay? So type A could be applied as a condenser fan cycling control. If the pressure drops too low, the fan will not run. Condenser fan, this is also known as a low ambient control. Type B, low pressure cutout control. Normally closed. If the pressure drops too far, like a refrigerant leak or something, it's going to open up and cut out the compressor to protect the compressor. Type C, okay, if the pressure drops, it's a normally open, okay, high pressure control. Okay, as the pressure drops, it's going to close. Type D, high pressure switch, normally closed. Okay, this is a high pressure cutout. If the pressure goes too high past the set point, it's going to open up and shut off the compressor. High pressure controls open on a rise in pressure. If you hold a high pressure control in your hand at room pressure, it is closed. It's primarily used as a safety device to shut off a compressor if the pressure rises too high. Now again, this is an important troubleshooting thing. If you have a high pressure control that you suspect is bad, take it off the system, pull it to room pressure, and it should be closed. In other words, when you put your meter across it, ohm meter across it, it should read 0 as the ohms. Most high pressure controls have a manual reset. This is to prevent it cycling in an unsafe condition. So this is an example of a wired high pressure switch. Okay, we come in from line to neutral. We have a disconnect. We have a fuse. The high pressure control will open on a rise in pressure. It protects the compressor in this case if the pressures go too high. Couple examples of high pressure controls. We have the type you most often see on residential and commercial air conditioning systems, and we have a type you see on refrigeration. Okay, we have manual reset levers. This one may have a button on the end of it. This is a Ranco pressure switch. This is what we have on our training boards most often. We have a cut out and a differential. Okay, you notice there's no cut in. The cut in is based on the differential. And this is just with a top off of it. Again, we have this is a combo pressure switch. We have the low pressure side on the right side. We have the high pressure side on the left. You can tell it's the high pressure side because there's a manual reset. Low pressure switches are used to sense a drop in pressure. Most often the low pressure switch is used to sense a loss of charge of refrigerant. The low pressure switch is also used to control the compressor in a pump down system, as we talked about at the beginning of this presentation. It is not desirable to run a system with a low charge because the compressor motors use refrigerant to cool the windings. If the system goes into a vacuum because of a leak, it may also pull air and non-condensable gases into the system and cause further damage. We never want moisture in a system, and air has moisture in it. This is an example of a low pressure switch. Again, we have a cut in and we have a differential. Okay, the cut out is based on the cut in minus the differential. We also have the set type that comes factory preset of a cut in and cut out and differential, and that's on the right. You see this very often in residential and light commercial air conditioning systems. This is a combo pressure switch, has both the low and the high. Again, the high will have a manual reset most often. Okay, and the low pressure control is on the left hand side, and it basically just has adjustments for cut in and cut out. Your enclosed contacts will either have a set of contacts for each or a shared set of contacts. The oil pressure safety switch is a very important pressure switch to talk about. It is a pressure differential control. It has both the low and the high pressure controls. The differential control takes the high and low pressure, compares the two numbers, and comes up with a net pressure. Anytime we talk net, it's the difference between two numbers. The net oil pressure is the higher number minus the lower number. The net oil pressure is the usable oil pressure. So when we take a look at a compressor, we have our suction line and we have our our oil pressure. Okay, we take a pressure of our suction line, which is also the crankcase pressure. We take the oil pressure and we subtract the two. So in this case, my suction line and my crankcase, because they're connected, is at 70 psi. The discharge oil pressure is at 130 psi. That gives me a 60 psi net, or usable oil pressure. The oil pressure is caused by a pump attached to the crankshaft of the compressor. When the compressor is not running, there is no oil pressure. Because of this, the oil pressure safety contains a timer that delays the action of the switch for 90 seconds. In other words, 90 seconds after it starts running, the oil pressure switch will not do anything. Once that 90-second type countdown is done, we should have enough oil pressure for the switch to start sensing oil pressure. So when we look at a wiring diagram of this, we bring in line voltage, okay, and we bring in the compressor suction pressure, okay, that's my crankcase pressure. We have contacts that are normally closed, and they will open if the oil pressure drops too low. The oil pressure is measured between the suction side and the oil pump outlet. Most compressors must have a minimum of 30 psi of oil pressure. You'll always want to follow manufacturer's directions on this. Oil pressure safety controls have a manual reset. In other words, if the oil pressure safety opens on a compressor, we do not want it to automatically reset. We want it to shut the compressor off until a technician can figure out what's wrong with the oil pressure. This is an example of an oil pressure safety. Okay, we have one side that compresses to the oil line, another side that connects to the crankcase or the suction line, because those are identical pressures. We have our wiring components here, and we have a reset button. Most often that reset button is under the cover because we don't want customers to be pressing reset buttons. We have several pressure switch symbols. We do expect you guys to know them, and we want them to be used in schematics. Okay, we have a normally open pressure switch, normally closed. We have liquid level switches. That's so like liquid in a storage tank, water someplace. Normally open, normally closed. We have flow switches for air and water. This would be like air in ductwork or water in a water line. Normally open, normally closed. We also have timer contacts. Okay, these are delay on start, delay on closed. Okay, they're timers. And that covers our pressure switch and oil pressure safety. Okay, oil pressure safeties are pretty important on larger systems, larger compressors. Make sure you review if you need to. Pressure switches are used on just about every refrigeration and air conditioning system in the industry.